This is an additional video to go with 7.2, and you're working on taking integrands and being able to either use substitute or find a substitution for the integrand that might include some algebraic rearrangement. So there's 3 examples that we did do in class, but you might want to go through with me and just try again if you need the ideas. So one idea is we might complete some long division in order to carry out something to get my integrand simpler. Another idea is that we might complete the square in order to make something that my integrand or an integrand that could be easier to work with. And, pardon me while I get this out of here, we might use some factoring in the rearrange step. So let's start with some factoring. So factoring wise, that's the example we're going to look at here. If you try different u's here with the x squared plus 8x plus 16, all of your du's would involve x terms that you don't have. So as I'm thinking about how I could algebraically rearrange what I do have, I recognize that the denominator can be factored. So it's at least worth looking into the idea of seeing what that factoring might look like. And if you factor this denominator, it happens to be a perfect square trinomial, whose factoring would be the quantity x plus 4 quantity squared. Recognizing that, then I can take advantage of the fact that I could use substitute, making my x plus 4 expression the u value. X plus 4's derivative is just 1, so my dux differential could just be replaced by a dx. So I don't need to do anything special in the planning stage in order to get this to be equivalent. So I'll be able to make this 1 over u squared, or u to the negative 2, and then the du can quite literally replace the dx. Recognizing that I can take the integral of that had to have come from a u to the negative 1 that had a negative in front, plus a constant. And then on the resub stage, we're going to have the negative 1. Instead of u to the negative 1, I'm going to put it in the denominator, plus a constant. So the factoring allowed a u substitution that I did have the du components to take care of. In the second one, I can try factoring the numerator, and I can. It factors. It's the quantity x plus 2 times the quantity x plus 1. However, that does not simplify the expression or meet the challenge that if I pick any of the parts in there as my u currently, I would need a 2x as my du, or I wouldn't have other pieces accounted for. So in this second one, what we're going to try to do is some long division. This would not be my first choice, but after looking at the things that I've got, I don't see how I'm going to be able to make a u substitution, and I really don't have any other equivalences that will help here. So what I'm going to try to do is divide this out first. Not try to, I'm going to. So my long division, I'm dividing by the quantity x minus 1, and I'm dividing the quantity x squared plus 3x plus 2. Carrying out my long division, I will need an x factor here so that x multiplies by x minus 1 and uses up x squared minus x of this expression. Here's where I'm going to change colors kind of quickly. I have to subtract everything that I just used. So subtracting the x squared leaves no x squareds. Subtracting the opposite of x leaves me with 4x plus 2. And then I'm going to try to divide again. X minus 1 divides into 4x plus 2 4 times. So I will have 4x minus 4 here. But again, I need to subtract. That's how long division works. And see what remains. And I am going to get a remainder here. I'm going to get a remainder of 6. So what I know is that that 6 can no longer be divided by x minus 1. So therefore, I'm going to take this and bring it up and say, well, it still needs to be, but that's the simplest expression I can make of it. And the reason that you did the long division is you're going to replace your integrand with that equivalent amount. That is the result of the division. So therefore, I can go over and take my integral and make it of the expression x plus 4 plus 6 over the quantity x minus 1, or 6 over the quantity x minus 1 like that, dx. I used long division to rewrite the expression I needed to integrate in hopes that now I'll be able to see good antiderivatives for this. And I do. The integral of x would be 1/2 x squared. The integral for 4, 4x. And the integral for 6 times that would be 6 times the natural log of x minus 1 and plus a constant. So I was able to get the integral of my original expression by changing its form using long division. And finally, completing the square. Might have been a while since you completed the square, but completing the square is kind of going back to the idea of what we had in this first one, that if the denominator were a perfect square or other things I could work with, I might have a better idea of being able to get the integral. However, that denominator is not a perfect square trinomial. It's off by a little bit. So if I were to try to factor that denominator, I could factor the x, so I could factor these first two and actually most of this last one. If I had x plus 8 quantity squared, just thinking out loud, that would be equivalent to x squared plus 16x plus 64. Well, I have 65, so in the denominator I have one more than that. So I'm going to go back and rearrange my integrand here. I'm going to bring the 7 out front because at the moment it's not bringing me any great joy. And I'm going to rewrite that denominator with a completed square and the extra that was there and bring down my differential. In looking at this, I see an inverse trig expression in here. So what I'm noticing is it's something squared plus 1 in the denominator. So if I were to make my u x plus 8, my du would just be dx, which is handy. And I could rewrite this, the little u substitution, as 7 times the integral of 1 over u squared plus 1 du. In doing that, I see that I could get for my integral 7 times the inverse tangent of u plus a constant. And in my resub stage, I could get 7 times the inverse tangent of x plus 8 plus a constant.